Welcome to Section 2, Introduction to Fraud Detection. This is Lecture 3, What is Anomaly Detection? So if we look at this image with basically a massive tray full of eggs, the majority of them are white, as we know, and we can see one that sticks out, which is the red one. So in a sense, this red egg would be anomalous in relation to all of the other normal eggs that we know to be white. And this can be cast as a machine learning problem in a sense. If it's fraud detection that we're speaking about, we have very few fraudulent transactions. We have a lot of normal transactions. But how do we go about training a model that can find these red eggs specifically within a sea of predominantly white eggs or normal transactions? So by means of a definition, an anomaly can be seen as data that deviates substantially from the norm. And detecting anomalies, it's the process of identifying rare observations that differ substantially from the majority of the data from where they are drawn. So again, in a financial services context, by definition, if the majority of your transactions were fraudulent, you probably wouldn't be in business for very long. So you can rest assured that most transactions are good for a company to remain in business, because fraud is obviously expensive. There's a lot of penalties, there's a lot of reputational risks, etc., associated with it. But natural levels of fraud do exist within most organizations. You almost need to keep a very low baseline of fraud. It's naturally a typical problem to solve, but you can never eliminate fraud completely because the problem is complex. Bad actors are typically evolving. They've got more sophisticated methodology. And as an organization, if you don't have kind of 100% certainty in what is or isn't fraud, which you really are never going to achieve, typically you're going to apply some sort of operational process to circumvent the fraud, which is a kind of friction which might make the customer experience a little bit slow. Certain customers might not have access to features on your website, for example, and that also has a negative feedback or a negative experience on the customer. So in some sense, you're never going to apply full friction where you give your customers a bad experience. You'll have some throughput of customers. You'll allow them some leniency, but you're trying to solve this problem as intelligently as possible. So there's definitely a trade-off in that sense. And the applications of anomaly detection, I have spoken about fraud a few times. There are definitely many other applications. Some include intrusion detection, so website systems, things like that getting hacked from a network perspective. Fault detection, healthcare monitoring, systems monitoring, predictive maintenance. There's many application areas. When you think of the term anomaly, you might think of an outlier, and in some sense they are similar, but an anomaly, I'll give you an example of how that would differ from a numerical perspective. So let's assume a distribution of data. We'll just create a very simple histogram, and we'll assume a normal distribution with a mean of 100. And for example, standard deviation of 10. So we could assume that this is a subset of IQ scores from within a population of some sort. But we luckily can generate that with NumPy within Python. So that's a library for numerical processing, and we can specify our mu, or our mean value, as well as our sigma, or our standard deviation. And we're just going to call them 110. And then from within NumPy, I can randomly generate a distribution of numbers, a normal distribution, as per these parameters that I've just set. So this mu value, the sigma value, and I would like to sample 1,000 data points. And then lastly, I actually want to plot this as a distribution. So I can make use of the matplotlib library, which is a very popular library for creating plots within Python. And it's as simple as calling the library, so the PLT object, we're going to initialize a histogram, we're going to supply the randomly generated normal distribution values, which is S, which is assigned to the variable S, and I'm going to bin them into 40 bins, and I want to present the plot. I want to expose it. Let's see how that looks. All right, so we've got what appears to be a normal distribution or a simple bell curve, what we know from statistics, with a mean value of 100 and then a standard deviation of 10. So one standard deviation would be here, two standard deviations, three standard deviations, etc. If we had to look for the outliers, in the sense it would be the data points that sit at the very far tails on either side of the distribution. So the very high IQs or the very low IQs, those would be our outliers for this particular data point, which within a data frame might just be a single column, right? But there are ways that we can, set some sort of a threshold and say, well, if the data is above 120 or 130, we can classify it as a outlier. And the same on the low side, we can also just set a threshold, which works pretty well. Then we also have the context of a box plot, and a box plot can print the very same data for us. So let us have a look at what a box plot does. So a box plot also represents the data, and it's a statistical technique for measuring the dispersion of our data. And it has a few different properties to it. So firstly, the orange line is the median of our data. And you can see against the y-axis that the value of 100 perfectly lines up with the median, which is what we set. Then we've got the minimum value, which is the 25th percentile minus 1.5 on the interquartile range. So it's a soft minimum. It's not the actual minimum value, but rather it's a soft minimum based on this formula. And this value is effectively this bottom line over here. Then we've got the maximum, which again is a soft maximum, which is the 75th percentile plus 1.5 times the interquartile range, which is this level up here. The interquartile range itself is effectively this big rectangular block in the middle, which ranges from the 25th percentile, so the 25th percent highest value, to the 75th percentile, and then it builds a rectangle. I mean, the shape can differ, it can become more of a square. And then these hard and soft, max and min values, outliers can fall beyond that. So if there's data points that fall beyond this maximum and minimum value, then these would be classed as outliers according to the box plot. So in this case, we've only really got one. Maybe there's a few that are overlaid. But if we regenerate our distribution again, because remember this is a random process, we've got a different distribution that's plotted. Here we see more outliers. And this is just outliers according to the box plot methodology. All right, so that works really well for a one-dimensional data point. So just a single column of homogeneous data. But for higher dimensional data, so for example, a set of features or a data frame of data, outliers and detecting those outliers becomes too complicated for those approaches, these simple approaches. So then we'd often need to take a non-linear approach in order to detect those outliers or these anomalies, as we need to determine how the data differs with each other and how the data from different columns in the feature space interact with one another, which ultimately adds to the predictive ability of the approach. So something that might seem like an outlier within a single column is easy to detect. I mean, we can just see it deviate very significantly from the distribution of the data, but an outlier in a broader context might be slightly different data in 2 or 3 or 4 different variables that collectively, when acting together, have this non-linear transformation that indicates anomalous behavior, but which is not easy to detect if you're just looking at each of the columns in isolation.